Good afternoon, year 9. The last time we have been discussing waves and wave properties, and now we are really starting with chapter 12 with sound. You must already know by now that sound is what type of wave? Indeed, it's a longitudinal wave. Okay, so how is sound produced? Sound is produced by vibration of objects. Yeah, it is actually a mechanical vibration in the air and other substances. Yes, sound can also travel through liquids and solids. Sound is a longitudinal wave in which the energy travels in the same direction as the particles within the wave vibrate. So this way, okay? Like we mentioned last time, vibration is like that, and the propagation, as we say, of the wave in this direction. So if we have like an air particle here, that means that the air particle is moving this way while the wave is propagating in this direction. Longitudinal wave, wave direction and vibration. Okay? As usual, I tell you that make some notes, pause the videos, and then we continue. Okay? Right. Sound wave. Well, we know that air has particles, and within the particles there are some vibration when the sound is. Now, how is it working in air? Now, in air, or it can be in liquids or in solids, yeah, we get regions of compression, so that means that the waves are compressed, and regions wherein we have rarefaction where they are pulled apart. So it's like this movement, okay? Compressing, rarefaction, okay? And that movement is traveling through the air, yeah, from one point to another point, okay? So what we see is we have here a loudspeaker, and the loudspeaker is producing waves, yeah? And then we get here compression of particles, and that is moving on, yeah? And we have a region of rarefaction, okay? So you need to know what we mean, how sound is produced, and that it consists of regions of compression and rarefactions, yeah, wherein the particles are further away from each other, okay? In the region of compression we have higher pressure, and in the region of rarefaction we have a lower pressure of the air, okay? Now the sound, the wavelength is actually the same as we see in a normal wave, yeah, that is in this case or the distance between the two compression regions, or you can even say the distance between the two rarefaction regions, okay? Just a question. Do you know how can we see sound waves? No, we cannot see sound waves. We need a special instrument. Do you know which instrument we use to actually represent sound waves? Think about it. Talk about that later. Okay, pause the video and again make some notes. Now, the range of hearing. What is the sound that you can hear? Yeah, if you have some loudspeakers or you have some earphones, it shows on the specification what is the range of frequency. Now, the range of hearing of humans is normally between 20 Hertz and 20 kilohertz. Yeah, if you have some good earphones, they should at least cover that region, okay? Now, when we are talking about a region that is below 20 Hertz, we cannot hear that. There are actually animals that can hear sound below 20 Hertz, like elephants. We call that infrasound. Oh dear. There are also regions above the upper level of our hearing, 20,000 Hertz, and we call that ultrasound. And you may have heard that there are some animals that actually make use of ultrasound, and they can hear above 20 Hertz, like bats. Okay? Now, when we get older, our ear is getting, it's like a mechanical machine that is connected to your brain and gets a little bit, well, worn out, yeah, and that will reduce the upper limit. Also will reduce the upper limit. But my limit, for example, is old person can normally hear around, let's say, 30 Hertz to maybe 15,000 Hertz. I want to tell you, I could do a test in the class and let you hear different frequencies, but most of you won't even hear 20,000 Hertz. Probably you will stop hearing a frequency of about 18,000, 19,000 Hertz. So over the years, your ears get damaged, and especially, of course, when you go to the disco or when you are constantly working in an environment of a loud noise, then it will damage your ear and it reduces especially the upper limit. Yeah. So my hearing, I can hear about 15,000 Hertz, but maybe later, when I'm a very old man, I can maybe only hear 10,000 Hertz, yeah? Okay? And especially people who are working in construction, yeah? And they are prolonged to a high sound volume over a long time, they really can have ear damage very soon, yeah? Okay, as I told you, some animals can hear higher than 20,000 Hertz, and some examples are bats that make use of sonar, and dolphins, and that's the way actually how they communicate with each other. Bats also use this to catch actually a prey. Okay? Oops. Dogs can hear between 40,000 and 60,000 Hertz. There are some special whistles that you can use. A dog will hear the whistle, but you won't hear it, okay? So make a note of that. Pause the video. All right. Okay, as I said, ultrasound is a frequency that is higher than 20 Hertz. Too high to hear by humans. We make use of it by, for example, locating fish, and we call that sonar. Okay, bats makes use of sonar. Okay, infrasounds are sounds inaudible to humans. We might actually feel it in our body. Yeah, if you go to a disco, you might feel that vibration below 20,000 here, but you don't hear it. Yeah, And some examples of infrasound elements. Why do you think they have such big ears? Yeah, simply to hear a frequency below 20 hertz. And for them, it's also a way of communicating over a long distance. Okay? So, don't forget what we mean ultrasound and what we mean by infrasound. Okay? Okay. Now, as I mentioned, sound can travel through different media. Okay? Maybe if you have seen on the Olympics, wherein you have this, how do you call that? This dance swimming, yeah, and they're swimming actually on music. Yeah, they have built-in loudspeakers in the swimming pool, yeah, so that they can hear the sound under the water. So yes, sound can travel. Okay. Sound travels the quickest through solids. Why is that? So if you want to know if a train is approaching, you put your ear on the rails, yeah, and you could hear a train coming from several kilometers. Now, it's interesting to know why is sound traveling faster in solid. It's simply because in solids the particles are very close to each other. When there is a vibration, they are so directly connected to each other that speed is much faster. Yeah, one hits the other, hits the other, hits the other. Yeah, when we look at liquids, sound is still faster than in air because the particles are still close to each other, and then they can propagate the vibration pretty fast. Okay, yeah, and sound travels slowest in gases simply because sound, the vibration from one particle to another, when in air the particles are much further from each other, it takes time before it hits the other particle. So if we compare solids, now in solids we know particles are really close to each other, are tight to each other, yeah. So if this particle is going to vibrate, they are directly connected and it goes zoom, very fast, okay? When we look at liquids, particles are still close to each other, yeah? But now we know that they can move around, okay? So the speed in a liquid is a little bit slower than in a solid, but still very fast. Now if we look at the solid, you can imagine, yeah, you have here a particle, here, 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 here. If this particle is vibrating, it takes time before it hits the other one, the other one, the other one, so it's slow. So here, slow, relatively faster in liquid and fastest, okay? Yeah? In vacuum, without no particles, then we cannot hear any sound. So, if I was on the moon, if I would be on the moon as an astronaut and I would like to communicate with another astronaut, well, I can scream whatever I want, but I cannot hear, the other person cannot hear me. So they make use of radio communication, okay? Yeah. Now, And to demonstrate this, unfortunately, I don't have the bell jar experiment, but how does it work? What we do is we put a bell in a glass jar. Wires are connected to the bell. We connect a vacuum pump to the bell jar. Yeah. The bell can still keeps working, and meanwhile, while we are pumping out the air out of the jar, you will actually hear that the sound gets softer, 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 up until the end. There are no air particles anymore in the bell jar, and sound cannot travel through the vacuum to the sides, yeah, because we need particles, so we won't hear the bell anymore, yeah. So this experiment clearly shows that you need a medium to transmit sound, yeah, okay. And when you do this experiment, you clearly can see that the bell is still working, yeah, but you won't hear it because there are no particles in the jar, okay? So, again, make a note of this. Okay. Reflection of sound. Echo, echo, echo. Yes, echo. Ever heard an echo? Ever wondered why you hear an echo? Well, it's pretty simple, and if I would be standing in the mountains and I would be screaming, I would hear my voice probably 1 or 2 times a couple of seconds later. Yeah, we call that an echo. Simple fact is that sound reflects the walls and bounces back and comes again to my ear, okay? So, this is an interesting. A misguided child shouts at a nearby cliff and hears an echo 1.4 seconds later. How far away is the cliff? And take the speed of sound as about 340 meters per second now. This is a typical IUCSE question, and we have to be very careful what we are actually doing here. Now, here's a person, and here is the cliff. Okay? This is the distance. Yeah? Now, this person is making sound. Traveling. How is the sound traveling? The sound is traveling from this person that says, Chelsea! Then, it hits here, the cliff. Okay? Then, what is going to happen with the sound? It bounces back. So, interesting to know, what does this 1.4 second represent? That is the time the sound travels this way and this way, okay? So, we can now calculate the total distance the sound has traveled, okay? So, which formula can we use for the speed and distance? Yeah, distance is velocity times time. D is 340 meters times 1.4 is, be careful what we say here. So actually I should say when I refer to this distance, 2 times d, because it's going one way to the cliff and then one way back. So, and this is a mistake many students make. So 2d is 476 meters divided by 2 is 238 meters. Now, please be aware that you don't make that mistake by just using the distance v times t, and then you forget that you actually, the distance represents from the person and then to the cliff, so that would be actually the 2d, okay? So, again, the sound travels to and from the cliff, total distance 2d, speed is distance over time, distance is speed times time, it's 340 times 1.4, 476 meters, so the distance is actually 238 meters, okay? Okay, I move on. Refraction. Okay, what is sound refraction? That's interesting, yeah? Now, when sound is traveling from one medium to another medium, it's going to bend, yeah? So, there is, for example, yeah? Because, for example, if you are on land here you have cooler air, that means actually the density of the air is different. So we may say different medium means the sound is going to bend. Refraction we will discuss much more when we are going to discuss light, okay? So, the sound by A may be heard more clearly by person B than by C, because it's going to bend and hears more, okay? Yeah? So, in this case, we have refraction, yeah? Because it goes through a different medium. We don't discuss sound refraction too much, but we will discuss actually refraction of light, okay? Pause the video, make a note, as usual, and I move on. Okay, sound diffraction, yes. I might have shown it already in the last video what the diffraction is, yeah? Remember the last time that I was walking out of the door and that you still could hear me, because sound can travel, yeah, around the corner, or is going to bend, yeah, through an opening, yeah? Now, in general, the wavelength of a sound is 1 meter, and that is simple, the size of the aperture of a doorway. So the sound undergoes, remember what we discussed, diffraction, so it can travel around the door or around the corner, yeah? And that's why in some circumstances we can hear people even though we cannot see them, okay? Yeah? Even if you are living in your apartment, you have your window open, okay? There's a big chance that you can hear the people on the streets, and that is because sound diffracts, okay? So here's a good example, yeah? Someone is talking here, the door is open, can bend, and this person is in another room, and the door is also open, and it bends again, and these people can actually hear the people that are talking in this room. Yeah, even though they cannot see them, okay? That's an interesting question. Why does light not diffract as much as sound? It does diffract, but the wavelength of light is much, much, much smaller, and that's the reason why light does not diffract so much. Okay. Again, pause the video. Yeah. Okay. Now, in the IDCC, they will ask you how to measure the speed of sound. Can we just directly measure the speed of sound? No. What do you think? What do we need to measure the speed of sound? Indeed, we need distance. What else? We need time. Yeah? So, the best way is using a visible loud event. You could do this very easily with someone else, yeah? And you need two persons, okay? Now, one person is going to stand on one side. You're going to measure the distance between that person, and this distance should be at least 150 meters, okay? Then you have like clap, so that means the other person can clearly see what you are doing. At the moment that you are clapping here, the other person is starting the timer, and when she hears the sound, stop. That means you have the distance, you have the time, and you can calculate the speed of sound. Okay? So, yeah, use a stopwatch, and the stopwatch is to measure the difference between seeing and hearing event. And when you know the distance and the timing, you can calculate the speed, yeah, and this over distance over time, yeah. Remember that the distance should be very large, actually, because the time it takes from travel from one to one other person is pretty fast, so you're going to have a lot of errors when clicking on your clock, okay? Okay. Before we move on, there's another method, yeah? Remember, we discussed an echo, yeah? You can actually do it yourself, yeah? If you are in a wide open area and you want to, you have a mountain or you have a big building, you measure the distance between you and the building, yeah? Then you make a hard sound, and at the same time you click the timer, and when the echo is coming back, you stop the timer. Then you know the time, you know the double distance, and you could calculate the speed of the sound. Okay? Alright, that's the first method. Oh, I think I talked about it. Alright. A group of students measure the time taken between seeing and hearing another student 250 meters away. Clashing two pieces of wood together, they obtain the following timings in seconds: 0.73, 0.78, 0.69, 0.81, 0.77. Use their measurements to obtain a speed of sound estimate. So stop the video and calculate the speed. Right. Average time. You add up the time divided by 5. You have the average time. Speed distance over time, 250 over 0.756 seconds. 4,000 meter is 331 meters per second. Okay? All right. Another way is, as I told you already, making use of echo. Yeah? Facing a flat vertical surface at least 50 meters away. A person clashes two pieces of wood together. This person should try to clap the pieces of wood into time while the echo they hear coming back from the flat surface. Yeah? Another person claps 20 times on a stopwatch, and they should count 0 to 20 Yeah, and then you measure the distance, yeah, and you have the total distance is 2d, and then that will be 20 times 2d. It's a way of doing that, and then you can calculate the speed is the total distance divided by the time over the 20 claps. Okay? Try to do this question. Pause the video. In an experiment, to measure the speed of sound by the echo method when the student stands 75 meters away from a wall, 20 claps are heard over a time of 8.77 seconds. Calculate the speed of sound. Okay. Total distance traveled by the sound is 20 claps. Double distance times 2 times 75. Then we know the total distance. Yeah. The time is recorded as 8.477, and then we can calculate the speed, which is equal to 342 meters per second. Okay? Right. Now, in general, you need to know at least some values of the speed of sound, and what at least is a normal speed of sound when it is in air, when it is in a liquid or water or in a solid. Okay? In air, 330, normal standard. 20 Celsius degrees. You see, when the temperature changes, the speed changes. Fresh water, let's see. You see, much faster. 1,497. Seawater, even a little bit more dense, 1,560. And steel, 5,000 meters per second. Yeah? Even normal aircraft will not reach this speed. Okay? And in vacuum, the speed is, of course, rien, zero. Yeah? Nothing. Very well. So, this value is important. You may say in a liquid, and you see, yeah, increase, yeah, between these three: solid, liquid, gas, liquid, solid. Okay. So again, for you guys, it's easy to make some notes. Just pause the video, yeah, and make some notes. All right. We don't discuss this, but it's interesting to know. Yeah. It's actually Mach number is the object speed divided by the speed of sound. Okay, you might have heard about it. Okay. Thunder and lightning. Now, how do I know how close a storm is when it's storming and we have thunder and lightning? Okay. Now, light travels at a speed of about 300 kilometers per second. So, at the moment when there is lightning, you will hear it directly. Yeah? Now we know that the sound in air is about 330 meters per second. So it will take a while before the thunder is heard. So in this case, 15 seconds. Okay? So you could actually calculate the distance between you and the thunder and lightning. Okay? We know that the speed of sound in air is about 330 meters per second. You know the time, you can count it, and then you can calculate the distance. Yeah, and in this case, the observer is about 3 miles away. So what I always do is, when there is thunder and lightning, and I want to know if it is approaching, I see the lightning and I'm going to count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, for each second, more or less represents 1 kilometer. Okay? So I can actually know when a storm is approaching or not. Okay? Yeah? No, we don't do miles, huh? We do kilometer. Alright. What would be the thunderclap? Thunderclap is heard 12 seconds after lightning flash. Calculate the distance to the lightning flash. Yeah, and we may use the speed of sound of 340. Pause it and try to calculate. Okay, speed, distance over time, distance, speed times time, 340 times 12 is 4,000 meters, 4 kilometers. Okay. Okay. Coming back to the beginning, yeah, where I was asking you, how can you actually see sound? Now, sound you cannot see, you only can hear it. So, but how do we see it in waves? No. What you do is we use an oscilloscope, yeah? An oscilloscope is a device that with a microphone attached, it can display a sound wave, okay? So it will display on the screen, yeah, it will display the regions of refraction, the regions of compression. And we get nicely just the same as we discussed in the waves in our last section. Yeah, we can see a nice wave, and from that we could actually find the frequency if we know the time divisions here, and we can find the amplitude. We could calculate the frequency or the time period, okay? So oscilloscope is used to represent or to show or display a wave, okay? Okay, the loudness. What do you think? The loudness of a sound. How would that represent in a wave? Okay, let's look. Yeah? When the amplitude of the sound increases, the loudness of the sound increases. Okay? So, for example, this wave is quiet. When we increase, it's loud. Okay? Much higher amplitude. Remember, we measure the amplitude from the rest point. Okay, from the middle. So from here to here, or from here to here. We see that the distance is much higher. Okay? The pitch. Who knows what is the pitch? Pitch. The pitch actually tells if the sound is high or low. So where is it related with? It is related with the frequency. Okay? So the pitch of a musical tone increases with the frequency. Okay? If we look again at the low pitch, where do we have to look? How can we see if it has a lower frequency than this one? Simply because the wavelength is smaller, meaning there are more vibrations per second, meaning a higher frequency. Yeah? In musical terms, doubling the frequency increases the pitch by 1 octave. Before the A above the top C will have a frequency of 880 Hertz. Well, not a musical person, but people who work, who play an instrument, they know what I mean. So again, low pitch, low frequency, wavelength bigger, high peak, high pitch, high frequency. Higher sound, okay, or higher pitch.